Okay, we're doing a screencast of a few Mastering Physics problems, number 28, 33, 28, 30, 33, and 38. So I'm going to go ahead and do those on the screencast, and hopefully that helps you guys understand how to do them. So this is number 28. It says, approximately what temperature does the average random kinetic energy of diatomic nitrogen molecule in an ideal gas equal the macroscopic translational kinetic energy of a single copper atom from a penny dropped from a height of 1.9 meters. So this would be UG equals the average kinetic energy in of a nitrogen molecule. So first let's find the UG, this gravitational potential energy that's dropped from the atom dropped from a height of 1.9 meters. That's mg delta H. So you drop the penny from a height of 1.9 meters. We need to know what the mass of a single copper atom is. Copper is at about 64 on the 63.55 grams of molar mass. So a single atom is going to weigh 64, I guess, times 10 to the negative 3. That's kilograms. We want to have this in kilograms. And divide by Avogadro's number, that's the mass of a single atom. That's going to give you a big number. Hang on just a second. Or, I'm sorry, a tiny number. Okay, that's 1.06 times 10 to the negative 25th kilograms, because we want our answer in joules, and to have the answer in joules, you got to have your mass in kilograms. So I'm going to have that 1.06 times 10 to the negative 25th times, I'll use 9.81 since this is Mastering Physics. It probably wants an accurate number, so I'm not going to round off to 10. Let's see what that gives us. Okay, what I got was 2.03 times 10 to the negative 24th joules. That's how much energy, gravitational potential energy, that the copper atom had at the top of the 1.9 meters. If it gives it all up to kinetic energy, so now that's the average kinetic energy of the N2 molecule, and that is 3/2 kT, right? So what temperature would that diatomic nitrogen molecule have to have in order to have that many joules of kinetic energy on average? So we're just going to solve for T on this. All right, so 2/3 times 2.03 times 10 to the negative 24th times 1.38 times 10 to the negative 23rd, I think it's K. That's going to give me T in Kelvin. Let's see what we get. Okay, you might have noticed that I made a little mistake there. I shouldn't have multiplied by 1.38 by the K. I should be dividing by K on both sides. So I'm dividing by K, and I got 0.098 kelvins or 0.10 kelvins. Oops. Let's see if that works here. See if I can type in here. I'm not sure I can. Let me activate my window. Let me check to make sure that I can activate my picture here. I think I lost my connection on that web page, but the correct answer is 0.1 kelvins. So that is a really small number, all right? That is a almost absolute zero. So a penny atom dropped from 1.9 meters, a copper atom has a nitrogen molecule, a diatomic nitrogen molecule would have to be almost at absolute zero to have as little kinetic energy as that penny atom. All right, let's do 9:30 on the next one. Okay, for this one, it says there's a balloon ride. The balloon has to be inflated to a volume of 1,500 cubic meters of helium at sea level. It'll rise 12 kilometers where the temperature is negative 52 and the pressure is 20 kPa. The initial gas temperature and pressure are 299 K and 1 atmosphere is pressure. which is the same as 1.01 times 10 to the 5th pascals. I think the book, for the most part, uses 1.0 times 10 to the 5th. And it gives you some information here about what the temperature and pressure is at altitude. But what it asks you is how much helium should we put into the balloon? So you're trying to find N, number of moles, but I think what it probably wants is mass in kilograms. So we'll find out how many moles, and knowing what the molar mass of helium is, we'll figure out a number in kilograms. That volume, or that amount of helium, isn't going to change at the higher altitude. So that's kind of a distractor that they gave you all this information at the higher altitude. What it does tell you, since you're going from 101 kPa to 20 kPa, you're cutting the pressure in 1/5. You can imagine what the volume is going to do. Since pressure and volume are inversely related, the volume is going to go up by a factor of 5 if pressure goes down by a factor of 5. First, let's figure out, using PV equals nRT, let's figure out the number of moles of hydrogen. So we've got PV over RT. So I've got 1.01 times 10 to the 5th times 1500 divided by 8.31 times T is going to be 299. Let's see what kind of number we get for number of moles. So I get 60,973 moles. Of helium. And the molar mass of helium is 4 grams per mole for diatomic helium. Oh, no, helium is not diatomic, is it? It's monatomic. There we go. Okay, so that would be 0.004 kilograms per mole. So if we want to know how many kilograms, we're going to have to multiply 60,973 times 0.004. And I get 244 kilograms of helium. Let's see if we can make this work. It is not going to let me type that in to get the satisfaction of the green. Let me check my answer real quick. Okay, I looked at the solution view here, and the answer is 240 because it's to 2 sig figs. There was some rounding, and I didn't actually use this number right here. I used the number in my calculator, so I was off by 4 kilograms. But that's how you do that one. Again, this was a distractor up here about the 20 kilopascals and negative 52 degrees at altitude. That doesn't change the number of moles that you needed to put in it to fill the volume of 1,500 cubic meters at ground level. All right, let's move on to number 933. Okay, 933. Concentration of particles. Assume they're neutral hydrogen atoms. Let me turn on my neutral hydrogen atoms. Interstellar gas is 1 particle per cubic centimeter, okay? So N is 1, and V is 1 cubic centimeter, and the average temperature is 16 Kelvin, okay? 16 kelvins. And we want to know what the pressure is. So we've got everything we need for PV equals nRT, nKT, let's say, because they gave us number of particles, so we'll use big N and little k. We need to convert this into cubic meters, all right? So 1 cubic centimeter, and in 1 cubic centimeter there are, there are 100 cubic centimeters in 1 meter, so I need to divide that by 100 3 times, all right? So I'm going to get 1 over 1 million, so 1 times 10 to the negative 6th there. All right, so pressure is going to be N, which was 1, times K, 1.38 times 10 to the negative 23rd times 16, all over 1 times 10 to the negative 6th. All right, cubic meters. And the pressure is going to come out to be in pascals. Let's see. I get 2.2 times 10 to the negative 16th pascals. Let me double check that, see if that looks right. Okay, but they want it in atmospheres, and so 1 atmosphere is 1 times 10 to the 5th pascals, so I have to divide by 10 to the 5th. So I'm going to get a really tiny number here. So the pressure in atmospheres, because you notice there, they want us to compare to atmospheres here. Actually, I can give my answer in terms of pascals most likely, but we have to compare it to atmospheres in part B. So I get 2.2 times 10 to the negative 21, obviously, because all I'm doing is, that's a 5 right there is my exponent. Doesn't look like it, but subtract 5 from 16 because it's in the denominator, and you get a negative 21. So it is much smaller than the minimum value for the best vacuum on Earth. So the best vacuum on Earth can't come close to what space is like. Okay, here's the solution view. So it shows us that, looks like we're good. That's pascals, 2.2 times 10 to the negative 16th pascals. Converting into atmospheres, it's a lot less than 10 to the negative 15th. Okay, let's move on to the last one, 938. All right, this is 938, and this is the last one. The pressure of the air in a diver's lungs when he's 20 meters under the water is this right here, about three times atmospheric pressure. Every 10 meters you go down, it adds another atmosphere. So at 10 meters, it'd be 2 times 10 to the 5th. 20 meters, it's 3 times 10 to the 5th, and so on. So they give you a volume of the air, 4.2 liters, and it's at a temperature of 20 C or 293 K. How many moles of air should the diver exhale while he's going up to the surface where it's at 101 kilopascals, or atmospheric pressure at the surface? Well, you have to assume something about the volume of the air in the lungs is that it stays the same. So you have to assume that delta V is 0, so that initial volume and final volume of the of the air in the diver's lungs is the same. So let's figure out how many moles are in the lungs to start with at 20 meters below the water. Then we'll figure out how many moles would have to be at the higher pressure, when the diver is at the surface, and the difference between those are the moles that the diver is going to have to exhale. Okay, so let's figure out, since PV equals nRT, then N is going to be PV over RT. And this is 3 times 10 to the 5th pascals times a volume of 4.2 liters. We need this in cubic meters. So I'm going to go ahead and look up how many liters are in a cubic meter. So in the front of the book, which I think you may have in the front matter, I don't know if you have this. In my hard copy, I've got some conversion factors. You can look it up on Google easily. You have to divide by 10 to the 3rd. Okay. So divide 4.2 by 1,000. And 8.31 is R times, that should be multiplication dot, times 293. And that gives us the number of moles at the depth. Okay, so N at depth is, so I get 0.517 moles at 20 meters below the surface. Again, we had to convert liters to cubic meters. So that's how many moles of an ideal gas, whether it's air or whatever it is. Sorry about the announcement there. That's how many moles would have of any ideal gas would, at that pressure and that volume and that temperature, that's how much space they would occupy. So now we need to find at the new pressure, so we'll call it N prime. So now this is, volume is going to stay the same, so we're still going to have the 0.0042, but my pressure now is 1 times 10 to the fifth. Basically, everything's the same, right? It's just 1/3 as much. So all we have to do is take, we're dividing that number by 3. All these other numbers stay the same, stay constant. So just divide your number of moles by 3. So that would give us N prime. So the changed number of moles that the person has to exhale is going to be 0.517 minus 0.517 over 3. Let's see what we get. I get 0.345 mole. Let's see what the answer tells us. Okay, looks like we're good. That is 0.345 mole is the correct answer. If you have questions about any of these that we went over, you can come in and see me before school or after school. Also, if you have questions about other ones that I didn't do, let me know, and maybe I can do a quick screencast for that. Okay, I'll see you tomorrow in class.